Hello, welcome everybody. Now today we will discuss how to design the ALU circuit. As all of you know that ALU is a very complex circuit. So for better understanding, I will give an example to construct a 4-bit ALU circuit. So ALU is a digital circuit that is used to perform all arithmetic and logic operations. So it is basically the fundamental building block of our CPUs. So modern CPUs contain very powerful and complex ALU. Most of the operation in the CPU are performed by ALU. The control unit tells the ALU to perform what kind of operation, and the data is provided. Then ALU carry out the operation and find out the result. And the result are stored in the intermediate output rate. So arithmetic, it has two different units. One is arithmetic unit, one is logic. So arithmetic units are the arithmetic units carry out the micro operations that can be implemented in one composite arithmetic circuit, which requires a parallel adder. So by controlling the data input to the adder, it is possible to obtain different types of arithmetic operations. So in arithmetic unit, we need only two main circuits, full adder and multiplier. So with this circuit, we can perform all these types of operations. We can perform normal addition operation. We can perform addition with carry operation. We can perform subtraction with borrow operation, which is commonly known as ones complement addition operation. The normal subtraction operation, which is commonly known as subtraction operation with the help of two's complement addition. We can transfer one value from one place to another place. We can increment any register content. We can decrement any register content. So this is the block diagram of the arithmetic unit of the ALU. So here you can see, as this is the example of 4-bit arithmetic circuit, so 4 different full adders are used. First full adder at the lower order bits x0 and y0. Next x1, y1, next x2, y3, next x2, y. And ultimately d0, d1, d2, d3, all the sum bits are generated and the ultimate carry C out is also generated. Now, as the truth table reveals, we have to perform a different operation. That's why we have to choose the operations. That's why we have to use marks. So we are using 4x1 marks here. And for 4x1 marks, we require only 2 select lines. So select lines S1 and S0 is connected to every mark. So based on the value of S1 and S0, we will definitely find out what operation will be carried out by the arithmetic unit. So if S1, S0 are 0, 0, then input line 0 of every mark will be selected. And you can see from the picture that input line 0 for every mark is directly connected to the B input. And on the other hand, all the A inputs are directly connected to the full adder input x0. So basically, we are performing A plus B. Now, there is another input Pin, you can see in the top of the picture. So if in that case Pin value is 0, then we are just performing the normal addition A plus B. And this arithmetic circuit will provide the corresponding output. Now, with the same condition of S1 and S0, if we change the value of Cin is equal to 1, that means we are able to add, we are able to perform addition with input carry. So, add with carry is performed here. Now, if S1 and S0 are now 0 and 1, so this will select the second input of every marks. That is, input line 1 of every marks will be selected. And you can see input line of every marks is connected to the complement of B input. So basically, as a marks output, we will get B0 bar, B1 bar, B2 bar, and B3 bar. And if Cin is equal to 0, now that means eventually we are just going to add A plus B complement. So we can definitely find out the result of subtraction with this, and this is commonly known as subtraction with the help of one complement. Now in the same scenario, if we change the value of Cin is equal to 1, that means we are able to perform the operation of A plus B bar plus 1. So as B bar plus 1 represents the 2's complement of the input B, that means we are able to perform subtraction with 2's complement addition operation. So you can see all the combinations of addition and subtraction can be found with this arithmetic circuit. And as multiplication is nothing but a repetitive addition and division is nothing but a repetitive subtraction, so all the basic arithmetic operations can be done with this arithmetic. Next, if S1, S0 are 1, 0, that means third input of every marks will be selected. That is, input line 2 of every marks will be selected. And you can see input line of 2 is connected to input 0. That means we are not giving any input values to B. So only A0 is transferred to X0. A1 is transferred to X1. A2 is transferred to X2. A3 is transferred to X3, and so on. Now, if value Cin is equal to 0, that means we are just transferring the value A to output line. This is called transfer A. Now, in this situation, if we change the value of Cin is equal to 1, that means we are just adding A plus 1. So here we can increment the value of it. Now, a very interesting thing occurs when S1, S0 are 1, 1. H1, S0 are 1, 1 means last input or fourth input of every marks will be selected. So input line 3 of every marks is connected to 1, which is basically bound by inverting the input 0. So A plus 1 will be performed by the arithmetic circuit. Now, if Cin is equal to 0, that will the arithmetic circuit will perform A plus 1, 1, 1, 1. Now, all of you will agree with that 1, 1, 1, 1 can be treated as a 2's complement of 1, which is represented with 4 digits. So if we trying to represent value 1 with 4-bit numbers, so it should be 0001. Now if we trying to find out the two's complement of this 0001, our output will be 1111. So that is propagated to Y input of the arithmetic circuit. And A input is directly connected to the X input of the arithmetic circuit. So basically we are trying to perform A plus 2's complement of 1. Now in the previous case, we have find out that A plus B 2's complement of B, which is equivalent to A minus B, then definitely we can represent this as a minus B operation. Now, in the same way, if A plus 2's complement of B is equal to A minus B, then definitely A plus 2's complement of 1 will be equivalent to A minus 1. That means we can find out the decrement operation. So ultimately, we will get the value of A minus 1. So in that scenario, if we change the value of C is equal to 1, that means we are trying to perform this addition. The last one, A minus 1 and plus 1. So that minus 1 and plus 1 will be cancelled out. Ultimately, we can be able to transfer the value of A to the output. Now, the logic diagram. Here a very simple logic diagram, logic circuit is described here with only 4 cross 1 marks. So we can able to perform only 4 logic operations, and or XOR and NOT, and all those logic operations will be indicated by the value of S1 and S0. If S1 and S0 are 0 0, and the operation will be performed. If those are 0 1, you can perform OR operation. If S1 and S0 are changed to 1 0, you can perform XOR operation, and for 1 1, you can perform NOT operation. But this is a very simple circuit, simple logic. But actually, with 2 variables, we can have 16 such logic operations. So for 16 such logic operations, we require 4 select lines. So 4 select lines will be able to choose any one input line out of that 16 operations. So here all the 16 operations are shown, which can be found with 2 binary variables. They are 0, x dot y, x dot y bar, x bar y, etc. So you can find out all type of logic operations here. AND operation, OR operation, not of x, not of y, NAND, complement, x plus y bar, y plus x bar, identity operation, exclusive OR operation, transfer operation, all types of logical operations can be found with this 16.1 marks. Now we are going back to the function table of ALU, how the function tables are generated. We require 3 select lines. When select line S2 is 0, all the arithmetic operation will be performed. If select line S2 is equal to 1, then all logic operations will be performed. So for all logic operations, C1 does not have any implication. That's why the value of Cin is equal to, can be treated as don't care. So this is the block diagram of complete ALU circuit. Here S1, S0 and S2, 3 select lines are used. Basically, S2 select lines will reveal what kind of operation will be going to perform, whether it is the arithmetic or logic operation. For value S2, all arithmetic operation will be performed. For value S2 is equal to 1, all logic operations will be performed. So in this way, arithmetic circuit and logic circuit can be clubbed together to construct a. So this is the complete ALU circuit, which is able to find out arithmetic operations as well as logic operations and two more operations that is commonly known as shift operation. We can shift the content of register towards left or towards the right. These two operations can also be embedded with ALU. So this is the end of today's discussion topic.